Our final presenter is Lucinda Li. Lucinda is a third-year graduate student in the research groups led by Dr. Nancy Love and Dr. Krista Wigginton at the University of Michigan. Her research centers around the risks and benefits associated with source separation technology and the use of fertilizers. So, over to you, Lucinda.
Thanks, Bradley, for the introduction, and thank you for all the other speakers in this session. Hope you can see my screen and hear me well. As Bradley said, I'm Lucinda. I'm a PhD candidate at the University of Michigan. I work with Dr. Nancy Love and Dr. Krista Wigginton to assess benefits and risks associated with urine diversion technologies and using urine as a fertilizer. So today I want to focus on the collection, so I won't go into the details and the motivation of why urine diversion, but rather focus on the urine diverting toilets. And we know that in order to implement urine diversion in a widespread scale, we may need to replace the conventional flush toilets that a lot of us in the United States use with urine diversion toilets or with the Marcel urinal. But today we're going to look at the urine diverting toilet. It's a flush toilet. And this shift in toilets from the conventional flush toilet to a urine diverting toilet may have significant impact on the user experience. And one particular component of the user experience is virus emissions from toilet flushing. And this is particularly important in the context of the current COVID pandemic, as well as future virus outbreaks. So today I want to present some preliminary data that I've collected in hopes to move this project forward to compare the virus emissions generated from toilet flushing in the urine diverting as well as the conventional flush toilet. All right. So as many of you know, when we excrete bacteria and viruses in the form of our excrement, urine, and feces, when we flush the toilet, some of those particles can be emitted back out of the toilet, and they generally do so in the forms of water droplets. They're characterized by size. We have aerosols. They're small droplets that evaporate and they travel with the air current. And then there are larger droplets that settle due to their size and cause more localized contamination. And I just want to spend some time here to emphasize that this study, as well as previous study, really focus on virus emissions during toilet flushing and not user exposure to infective viruses. And there are many external factors that impact user exposure to infective viruses during toilet flushing that we don't cover here, and many studies don't cover. There are many uncertainties. So I just want to put a disclaimer out that even if viruses are emitted due to toilet flushing, does not necessarily mean that the user exposure to infected viruses is high. So, as I said, this study focuses on virus emissions, and that largely depends on the type of toilet used. A couple parameters that drive virus emissions include flush energy, flush volume, and the toilet bowl design. In particular, the toilet bowl design is important when we're comparing the conventional flush toilet to the urine diverting toilet. So if it's not obvious, the picture on the right is the urine diverting toilet we have on the University of Michigan campus. It's pictured here again. And when we think about urine diverting toilets, we care because using this type of toilet in comparison to the conventional flush toilet may cause differences in how viruses excreted in urine and those excreted in stool may have different levels of emissions from these two types of toilets. One obvious reason for that is that the urine is being diverted from the toilet water. So viruses that are excreted in urine are physically removed from the scenario and not being put into the toilet water that will be flushed out and generate virus emissions when flushed. The virus types in urine differ from those in stool. And that's important also because urine and stool vary so drastically in their characteristics. One characteristic that is of particular importance is protein level. We know that when protein is excreted with viruses, it may impact how the virus absorbs to surfaces. So that depending on how much protein is excreted with the virus, you can have virus absorbing to the toilet bowl surface, or it may remain in the toilet water. So with that, the objectives of this study are to, one, develop methods to quantify total virus emissions, both in aerosols and droplets generated during toilet flushing, and two, compare virus emissions between the conventional and urine diverting toilets for viruses that are excreted in urine as well as in stool. We design experiments that will yield the total infective virus emissions from the toilets. We start by spiking the toilet with virus. In this study, we use viruses that are only infective to bacteria, and we use several types of viruses that represent several different structures of viruses. And so these viruses serve as surrogates for human viruses. Then we cover the toilet bowl surface area with a recovery surface, flush the toilet, and capture all the particles that have been emitted from the toilet during the flush into a solution. And finally, we quantify all the viruses in that solution using a method called plaque assay. This method essentially allows you to grow bacteria and virus on one plate and allows you to count the number of viruses on that plate. And I mentioned in my previous slide that protein level may have an important role in this understanding of virus emissions from the toilet. So in order to address that, we do this at the first step. We add in certain level of protein with the virus spike solution and compare that to no protein in the spike solution. And so the data I'll be presenting today is preliminary data. It shows these two scenarios for the two types of toilets. This first set of data is for comparing the virus emissions in the urine diverting toilet to the conventional flush toilet when there is protein present in the virus spike solution. So the figure I'm presenting, the y-axis is the log difference. So essentially what I did is I looked at the virus emissions, I normalized it to the virus emissions from the conventional flush toilets. And I'm plotting it on this axis. So 0 log difference means there is no difference between the emissions coming out of the urine diverting and the conventional flush toilet. Anything above 0 means that the urine diverting toilet is emitting more viruses. And anything below means that the conventional flush toilet is emitting more. The other thing to note with the y-axis is 1 log difference is equivalent to about 10 times of a difference in virus emissions, and 2 logs is about 100 times. Then on the x-axis are the viruses that we are studying. They represent different structures of viruses. And we see that in both of these viruses, the conventional flush toilet is emitting more than 1 log or more than 10 times viruses as compared to the urine diverting toilet. Now, when we take a look at the data where there is no protein present in the virus spike solution, the results look very different. So we're looking at the same graph. The high protein data is still here. I've added the no protein data in red, or the right, it's the right bars. And we see that the trend has flipped. Actually, we noticed 2 things. One is that the difference between the toilets is much smaller when there's no protein present. And 2, that the urine diverting toilet may be emitting more viruses when there's no protein present in the spike solution. And so I just also want to emphasize that this is preliminary data and more replication is needed. So more data is needed before we can draw any statistical statements from this data, but we can say there are some preliminary conclusions. One is that there may be significant differences between virus emissions generated from these 2 types of toilets, but that may also be heavily dependent on the amount of protein in the virus spike solution. And so with that informs our future steps and future work. Our next steps will be to look at realistic protein levels that match protein level in urine as well as in stool, and see how that falls, how that impacts virus emissions on the spectrum of no protein and high protein in the virus spike solution, as well as maybe look at different virus placement in the toilet if viruses are being placed at the front of the toilet where, especially for the urine diverting toilet, will be diverted out of the waste stream. And so with that, I would like to thank NSF for funding this project, my advisors, collaborators at Rich Earth, and all the members of the Environmental Biotechnology Group at the University of Michigan. And thank you all for listening.